In this lesson, we will continue with the material selection strategy, aiming to understand the steps that can lead us to the best material for a given project. We have seen how the choice of the best material is made by relating the design requirements of a product to the property profile of a material. The material with the best property profile will be identified through a series of steps. These consist of filtering out unsuitable solutions and, among the remaining ones, identifying the best solution. And finally, validating the choice based on knowledge related to the properties and specific characteristics of the material. We have already seen how the workflow is structured in several steps. The first step consists of providing a precise outline of the project specifications, identifying as main items the function of the product, the constraints to be respected, the objectives to be pursued, and the variables left to the designer's discretion. The following phases are filtering, ranking, and final validation or documentation. It is precisely these last three steps that we will explore in depth in this lesson. Let's talk about the first of these phases, namely the filtering or screening of materials. This phase is based on the constraints specified in the project translation. From the entire pool of materials, those candidates that cannot perform the required function will be eliminated, because one or more properties fall outside the imposed limits. Let's look at some examples of constraints and how these can be applied to material selection. A constraint may not be met when the value of a material property is below a set minimum limit. This is the case, for example, when a material does not meet certain minimum performance requirements, such as the component needing to operate at 250 degrees Celsius, or the component needing to withstand axial stresses of 150 MPa. In the first example, the requirement sets a minimum value for the maximum operating temperature, in the second for tensile strength. In other cases, however, it may be necessary to respect a maximum limit, for example, when you want to avoid using materials that are excessively expensive or too heavy by setting an upper constraint on properties such as cost or density. For qualitative or binary properties, materials are excluded using similar criteria. For example, one might select materials based on good, average, or poor environmental resistance, or for its electrical or thermal conductivity. Certain specific requirements can even take the form of a binary choice. A material can be completely transparent or entirely opaque, and it might be easily recyclable or not. At this stage, we refer to the material properties in terms of limits, that is, by setting a maximum or minimum threshold for properties that are important for the project or for specific types of behavior. This allows us to eliminate materials that do not meet the limits set by the design. Let's look at this from a practical point of view, working with material data, to see how these limits can be applied. When working with data tables, filtering can be done in two ways. The first is the more traditional method, which involves manually removing materials that do not meet a specific requirement row by row. It's definitely a valid method, but it's often time-consuming and prone to errors, especially when there's a lot of data and it's not well organized. The alternative, which is much more efficient, is to use tools like Excel pivot tables, which allow you to quickly filter, group, and analyze data. With just a few clicks, you can get a clear and concise overview of what would otherwise require time and attention. In software or interactive databases for material selection, constraints can also be applied graphically. This makes material selection much easier. The graphical screening approach uses horizontal or vertical lines that define the limits within which the desired properties must fall, automatically excluding materials that do not fall within the selected area. An intuitive way to visualize the properties is through a bar chart, where each bar represents a specific material. The length of the bar covers the range between the minimum and maximum value of a given property as it appears in the variance of that material. The position of the bar in relation to the constraint line is crucial. If the bar lies outside the limit, the material is discarded. If it remains entirely within the established boundaries, it is considered suitable and moves on to the next selection phase. An alternative that is much richer in information compared to the classic bar representation is the use of bubble charts. In these diagrams, materials are displayed on a Cartesian plane, where the axes represent two properties, for example, elastic modulus and density. Each material occupies a bubble on the chart. This bubble encloses the range of values that the property can take, outlining a characteristic envelope for that type of material. This approach allows you to apply multiple constraints at the same time. For example, you can set a minimum value for the Young's modulus and, at the same time, a maximum value for the density. The materials that meet both criteria will be found within the area defined by the intersection of these limits. Only the materials present in this admissible region will proceed in the selection process, while all the others will be automatically excluded. It's important to clarify that design constraints don't refer exclusively to properties and can also concern other important aspects. For example, the shape and geometry of the product, the type of material to be used, the manufacturing process, material availability, aspects related to environmental impact, and so on. Finally, it's useful to distinguish between two types of constraints. Non-negotiable constraints are essential characteristics that must be respected. And finally, negotiable constraints are important characteristics but not necessarily deal-breakers. Once the screening phase is complete, we'll have a solid foundation on which to compare the most promising materials in the next phase, known as classification or ranking. In this phase, the goal is to rank the remaining candidates based on which material best meets the set objectives. Which material will lead to the lightest solution? Which one is the most cost-effective? Which material will allow for the greatest energy savings? To do this, however, you need a criteria, and the tool used for this purpose is called the Material Performance Index. Performance indices are mainly determined by the objectives and may correspond to a single property of the material or to a combination of properties. Let's look at this with a couple of examples. The first will be a fairly simple example, a design case where constraints and objectives are not combined with each other. Let's imagine a level arm. It needs to be made from a material that is sufficiently stiff. With a Young's modulus greater than 20 GPa, and its shape and dimensions are already defined by the design. The objective, in this case, is to minimize the weight. But since the geometry is completely constrained, the only factor the designer can act on is the choice of material. The stiffness constraint acts as a filter and eliminates all materials with a Young's modulus that is too low, leaving only those that are structurally suitable. At this point, among the selected materials, you look for the one that allows you to minimize the mass. Since the volume is fixed, the mass depends solely on the density of the material. So the material performance index to be optimized will be the density itself. The lower it is, the better. Alternatively, we can say that the index to be maximized is the reciprocal of the density. The result doesn't change the lightest material. Among those that are sufficiently stiff will be the best choice for this project. Let's now see how this ranking operation can be carried out using tabular data or graphically. We can look up the properties in the data table by searching for the materials that maximize them. In this case, the best material is the one with the lowest density. We can also use pivot tables for sorting the data according to the properties of interest. Graphical visualization using bar charts or bubble charts allows us to identify the material with the best properties by moving along the axis corresponding to the property to be optimized, thus making it easier to directly compare the different options. In the second example, we analyze a case where constraints and objectives are interdependent. The project asks for a rigid tie rod, which is to deform very minimally only under the action of an axial force. The length of the bar is specified, while the cross-sectional area is a free variable. The objective is to minimize the mass of the bar. The options available to the designer are therefore the choice of material and the choice of the cross-section. The fact that a geometric variable, the cross-section, is free means that the mass can be reduced not only by changing the material, but also by reducing the cross-section, as long as the required stiffness is still guaranteed. This clearly shows how mass and stiffness are linked to each other. The cross-section affects both, and finding the right balance leads to a material performance index that combines multiple properties. Without going into the details of the calculation, which will be covered in a dedicated lesson, the result is an index given by the ratio of Young's modulus to density, that is, E over rho, also known as specific stiffness. In these cases, the material index involves two properties because the goal, to minimize mass, is coupled with a constraint, which is to limit deformation under load. Again, we can proceed in two ways, by using tabulated data or by using a graphical approach. First, we use material property tables to calculate each candidate's performance index. And thanks to tools like spreadsheets, it's possible to quickly sort the solutions, immediately identifying the material with the highest index. Alternatively, we can use bubble charts. Here, the two properties that make up the index are placed on the two Cartesian axes. Unlike for the indexes depending on just one property, where you simply move along one of the two axes, when dealing with a combined index, you move along a direction. Let's call it a mixed direction, represented by a line with a certain slope, in this case equal to 1. By moving the line upwards, we can identify the materials with the best performance. The precise definition of this line, how to choose the correct slope, and how to use it to compare materials are topics that we will explore in detail in a dedicated lesson. To sum up, material performance indexes are properties or combinations of properties that allow us to describe how closely a material meets the imposed objective. There are many different types, each tied to a specific design case, but in all cases they serve the same role. They are a criteria of excellence for classifying a material's performance in meeting a given objective. Now let's look at the final step, the one that allows us to validate our choice and to design the best material among our candidates. In fact, before making a final choice, it's important to assess the reliability of the selected material. This last phase, known as documentation, consists of an in-depth analysis of information related to the material. It relies mainly on supporting information, such as case studies, technical dossiers on the material, checking the material's availability on the market, and finally, market research. This final step allows you to further narrow down the list of selected materials, eliminating those that are unreliable or unsuitable, and it helps achieve a better match between the project's requirements and the property profile of the selected material. We can conclude that, from an operational point of view, material selection is a multi-phase structured process based on the constraints, objectives, and free variables established in the project translation. Initial screening eliminates unsuitable materials using min-max limits on critical properties, quantitatively and qualitatively per project constraints. The second ranking phase sorts the remaining materials according to a performance index, which can be based on a single property or on a combination of material properties, depending on the presence of interactions between objectives and constraints. The final choice then requires a documentary review to assess reliability, availability, and other practical factors, further refining the design decision. At this point, we have successfully matched the project requirements to the property profile of the best material among those available for selection.